No, just in the,
Be very careful.
all the carbons except the carbon that has the E on it.
Exactly. That carbon is sp3 hybridized, at least in the intermediate. So that carbon cannot be part of the resonance delocalization, but all the other 5 carbons are. And where are the positive charges? There's delta plus here, delta plus here, delta plus here. Those are the carbons that share the positive charge. Isn't that right? So sometimes you might see the intermediate drawn as that, which is the hybrid. Of course, it's for us to then recognize that the onus is on us to recognize, oh, then it's this carbon, and that carbon that are partial plus and partial plus and partial plus. That's for us to do. Everybody okay? This intermediate, whether you draw it as a resonance structure or you draw it as a hybrid, that's really a choice, is called a sigma complex. So the point is, the common thing you will see in all of these mechanisms is step number 1, benzene will come as a nucleophile and attack the electrophile to create a sigma complex. That's the intermediate. It is the sigma complex, and once again, it doesn't matter which one you use, whether you use the resonance hybrid or you use the one of the resonance structures. It's really a choice, and I'll show you what I mean when we write specific reactions. Once the sigma complex has been created, once the intermediate has been created, so starting with this intermediate, what does it need to do to now become the substitution product? Anybody?
Lose the proton.
Needs to lose a proton. That's all it needs to do. And how is it going to lose a proton? Who's going to come and take a proton? Who takes a proton? A base, some kind of a base. Now it doesn't need to be strong, by the way. It actually does not need to be strong. Why? Because the second step is extremely fast. Why? Because this is aromatic again, and aromatic is very stable. Very, very stable. So we don't need to really push this second step too much because it's going towards high stability. So, but some kind of a base, whatever, has to come in, take the proton so that the aromaticity can be created again. Aromatic is very stable. So the common thing you will see in all of these mechanisms as we write them one at a time is step number 1 is that the benzene will attack the electrophile, create a sigma complex. Once the sigma complex is created, the sigma complex will lose a proton to give us the product. Everybody okay? The difference is going to be the electrophile. Where is the electrophile coming from and who's the base? Because that's going to be the difference in all of the individual mechanisms. Questions so far? Okay, so then let's start looking at them one at a time. We'll start with halogenation first, and let's start. So remember the 5 main categories of electrophilic aromatic substitution reaction. So let's start with halogenation of benzene. Halogenation of benzene is when benzene, and right now we're just looking at plain old simple benzene, we'll add the details a bit later. Benzene is converted into halobenzene. Now, there are only 2 X halogens that actually undergo this reaction. Any guesses which 2? Exactly.
Bromine and chlorine.
X is either Br or Cl. So it's either bromination or chlorination, that's it. Not iodination, not fluorination, something else has to be done. Okay, the reagents needed. If we want to do bromination, then we are using bromine, of course. If you want to do chlorination, you need to use chlorine, but not by themselves. Nothing will happen if you just took benzene with bromine or benzene with chlorine. Nothing is going to happen because this reaction also requires a Lewis acid catalyst. Without that catalyst, this reaction does not go. So, if you're doing bromination, the catalyst to be used is ferric bromide, iron 3 bromide. But if you're doing chlorination, the Lewis acid catalyst
Aluminum.
is aluminum chloride. So bromination is bromine with ferric bromide. Chlorination is chlorine with aluminum chloride. Please make a note that aluminum chloride and ferric bromide are Lewis acid catalysts. They are not reactants, they are catalysts. But chlorine and bromine are reactants. Everybody good? Okay, so let's start with the mechanism.
The book says that you can do FeCl3.
Second, that's a great question. You can, but you will commonly not see that.
Okay.
Commonly, the Lewis acid used, commonly speaking, is just aluminum chloride instead of ferric chloride. I mean, same thing for that. Could we have just used aluminum bromide? And the answer is, at least on paper, sure. My guess is that it's probably because on paper it seems okay, but practically it didn't work out so well. So, the common ones are those. Okay, let's start with the mechanism. So let's start with chlorination, then we'll write the same thing for bromination and get a feel for the mechanism. So, step number 1 for chlorination is generating the electrophile. There's no electrophile right now in the system. So first we have to make the electrophile. That electrophile comes when chlorine reacts with the Lewis acid catalyst. By the way, what's a Lewis acid? Is that electron rich or electron poor? Is a Lewis acid electron rich? What's a Lewis acid? What's a Lewis base?
A Lewis base is.
I was thinking a Lewis acid accepts electrons and
Okay.
Lewis base donates, so
Exactly.
if that's true, the acid would be electron poor.
Exactly. Lewis acid is the one that takes electrons, electrophile. Basically, that is electron poor. And remember, aluminum is right below boron. Aluminum, a neutral aluminum, aluminum with no charge, does it have an octet? Does it? Has only 6 electrons. It's electron poor. If it's electron poor, it wants electrons, right? So if Lewis acid wants electrons, who's going to give it electrons?
The Cl2.
The Lewis base. The Lewis base gives electrons to the Lewis acid, creates a Lewis acid base adduct. Adduct just means 2 things added together. That's really what it means. So here we have the Lewis base, you have the Lewis acid, the Lewis base donates electrons to the Lewis acid and creates an adduct. What am I missing?
Charges.
Charges. Where and what?
You should have a negative on the aluminum and a
Positive on
positive on the chlorine.
Which one?
The one closest to the aluminum.
Agreed?
Yep.
That is the electrophile in chlorination reaction. Once that electrophile is created, this is where benzene then comes in. Benzene is the nucleophile. Remember, that's the electron-rich piece reacts with the electron-poor piece. Now, please pay attention. This is important. I'm just going to negative and positive. Which chlorine does the benzene attack? So, the benzene pi electrons attack the terminal chlorine, which causes these electrons to neutralize the positive charge. That breaks the Cl-Cl bond. Do you guys see that? Everybody? So, when that happens, what is being created as a result of this?
Carbocation.
The sigma complex. It is a carbocation, obviously. Yes, you're absolutely right. But we call it the sigma complex.
Sigma complex.
Because it's a very special carbocation. And once again, as I said earlier, you can either show the resonance structure or hybrid or one of the resonance. It doesn't really matter. That's a matter of preference. And isn't that right? Agreed?
Yep.
So instead of drawing the resonance structure, could have used the hybrid structure. Totally okay. Maybe next time I'll just show the hybrid structure instead of the resonance structure.
What did you
Everybody
say is
okay?
the name?
Say again?
The name of the
Sigma complex.
Sigma complex.
Okay? And then what does the sigma complex needs to do in order to make the product?
Get rid of a proton.
And who's going to take the proton?
A base.
Now, where is the base? So,
Oh.
the fourth Cl, which was causing aluminum to be negative, well, it can give us a chloride, which takes the proton and creates the pi bond. So, what are the products once that has happened? We get the chlorobenzene, we get the catalyst back, and what else?
Hydrochloric acid.
Everybody okay? But please notice, the only difference that we will see from one reaction to the other is step number one. How is the electrophile created? That's going to be the different from one reaction to the next. The second step, once you get the electrophile, this is going to be exactly the same from all of them. Guys, we all good? Everybody okay?
Yes.
Cool. Then let's write this mechanism for bromination. Same thing, but this time how about so we get that muscle memory in. So this time we want to write a reaction for bromination. Step number one is creating the electrophile. Bromine is reacting with the Lewis acid catalyst. Now, what is the bromine going to do? Anyone? What is bromine going to do?
Attach to the
Iron.
FeBr3.
So, bromine is going to donate electrons, right?
Yep.
And go to the Lewis acid, which creates the ADA.
How do you write that? Ada?
Okay, then I'll write it in a second. ADA. Add and charges, where what?
The bromine that makes two bonds has a plus charge.
The bromine with the two bonds is the plus charge and negative. Good. Please, you gotta keep track of charges. Okay, once we get the electrophile, that's when benzene attacks. Isn't that right?
Yep.
Now again, it doesn't matter which pi bond you show, which pi electrons, that's not important. What's important is for you to recognize that pi electrons are the nucleophile, oops, sorry, wrong, or what, wrong, yes. And go to the terminal halogen, which causes this bromine-bromine bond to break. That creates a sigma complex. Sigma complex, once again, one of the carbons of that pi bond will end up with the Br and it also has the hydrogen. The other one has a positive charge. And, oh, I promise that I'll keep the, okay, next one. And of course, we have and what does this need to do? The base is going to take a proton